Hi, good afternoon. Hello, everyone. I'm Krishna Kumar. I'm an assistant professor at UT Austin. So today our webinar is going to be on physics-informed machine learning, but I'm going to start off by giving you a very quick overview of what the Design Safe webinar series is, and then we will get into our physics-informed demo work. Okay, so I hope you can see the screen okay, and I'll try to have your chat open. Hey, all right, I'll post anything. I'll post the links again, but don't worry about it right now. Okay, so I hope you all know Design Safe. Design Safe is an NSF-funded cyber infrastructure for natural hazards community. We have webinar series. There's a lot of training materials that we do, including webinars, hackathons, and other programs. So this is part of our webinar series. Today we'll be talking about like physics-informed machine learning. We also have a Slack channel. If you're already part of Design Safe, you would have gotten an invite. If you got to know about this webinar through other locations, make sure you go to designsafe-ci.org /register. So that's designsafe-ci.org. Register, and you will be able to register for an account and also get access to our Slack channel. So we do appreciate your feedback. Please remind me to show this again towards the end of our presentation. Please leave a feedback. If not, just scan it right now so you have it open. This is the general feedback for all our webinar series, which are being organized in this semester. So please choose the physics-informed machine learning session, which is today, when you're completing this survey. Okay. All right, so that's me. I'm a faculty at UT Austin, and I mainly do AI-informed machine learning. Previously, I did numerical models. That's been my background, and now I do AI-accelerated machine learning. And I'm the director of an AI community in civil engineering called Chishiki AI. So if you want to become part of that community, you're welcome to join. That is also working together with Design Safe. So today we'll be talking about physics-informed machine learning. And mainly, how are we going to incorporate? I'll do this is more going to be like a two-part series. So you're going to get like the first part today, which is on the basics of physics-informed machine learning. And in the second part, later, you will see about doing inverse problems and heat flows with PDEs. Okay. All these training materials are recorded and they are published on YouTube. So you'll be able to watch all the archive materials on YouTube as well as on Design Safe. So go to Design Safe/Learning Center/training or tinyurl.com/designsafewebinars. That allows you to see all the materials. So this will also be posted soon. And Design Safe is a huge community. We have a Slack channel. So I hope you can see my entire screen. Yeah. So I've created a specific channel called 2024 Webinar Physics-Informed Machine Learning. If you're already part of the Design Safe Slack, I've invited you. If not, this is a public Slack, so you should be able to join here. So it's under Design Safe Slack Workspace 2024 Webinar Physics-Informed Machine Learning. I see a few of you joined, but I try to invite everyone who's been in Design Safe Slack already. And that's mainly, don't ask, I can't monitor multiple channels. So for now, if you have questions, just use the Zoom chat that I will try and monitor. But if you have questions later after the course is finished and you're all working on physics-informed machine learning, you want to help each other, please use that Slack channel so you can benefit from others in the same area. So we have everyone else also on Slack. So your support team is also on Slack. You have other researchers on Slack, so it's a great way to communicate with others. So make sure you publish your data on DesignSafe, share your ideas, experiences with us. All right. With that, let me. And this is our survey link, which I'll flash it up again towards the end of our session. So let's go here. I'm going to paste this again on Zoom. If you are just joining us, this is the link that should take you to a book. Let me know if you have any trouble getting to this location. I think I won't be able to see if you raise your hand right now. So please just put messages on chat, which I'll monitor periodically. Okay, so we're going to talk about physics-informed machine learning today. For that, we'll be using DesignSafe. I hope you all have a DesignSafe account. And the first thing I want to do, because there is going to be a lot of you, there are 117 of you right now. So we're going to start the servers up. We're going to use Jupyter Notebooks to do most of our hands-on activities. So I'm going to ask you to start Jupyter, but we're going to do it in stacks. So I'm going to stagger you. So if your surname starts, your last name, your surname starts from A through L, go ahead, go to DesignSafe, and in DesignSafe, you go to Tools and Applications. So this everyone can do until you click the Start button. So I only want you to click the Start button if your surname starts from A to L. And others, please wait. I'll let you know. We're not going to be behind the others. Okay. And then Analysis, click on Jupyter. So Analysis, Jupyter. And then make sure you're choosing Jupyter here. Don't choose the Jupyter CPU or GPU instance. We don't need that big an instance, and then click Launch. So you can also directly go to this link. So I'm pasting that again on Zoom chat. And then click Sign in with Jupyter Hub. That will ask you for your TAC login. And that's your DesignSafe/TAC login account. So log in, and then you'll be prompted with choosing an image. So you're going to go to the link I just pasted, type in your TAC user ID and password. And then when you get to this screen, make sure you choose the updated Jupyter image. You won't see 3 options. You're probably going to see only 2. And if you're already launched, it's okay. If you haven't yet launched, this is just for those who haven't launched the system. So make sure you click on and start your server. Okay. So this will launch Jupyter instance, and we will be able to log in and do some activities on that. Okay. So if your surname is A through L, this is, please go ahead and click on Launch or Spawn Jupyter. Others, please wait. I'll let you know. Otherwise, we will overcrowd our instances. Hopefully, everything will be fine. Okay. For others, make sure you're all logged in. And I'm going to start off by talking about what a neural network is, and then we will go ahead and talk about how are we going to incorporate physics into these machine learning models. Okay. So let's just go ahead and check. Yeah, you should be able to see this page, and let me know, or let us know in chat. Tracy is also here, and she will be able to help you if you have trouble logging in. Okay. So if you have issues, just message us on chat. Okay, I think All right, so if you're having trouble, just make sure to wait a couple of minutes and respawn. Again, so use the same link, try to refresh it and despawn again. Okay, initially you can just follow along with the notebook if with this book if things are taking time to start. Okay. Right. So we're going to start off with defining what a neural network is. A neural network is comprises of multiple neurons. So we are going to call those neurons. So like we have in human brain, we have multiple neurons. In machine learning, we call those things as perceptron. A perceptron is basically a single neuron, and we are going to see how to go from building a single neuron to a neural network, and then see how we are going to add physics into that neural network. Okay, so we're basically doing a neural network as a means of a regression type problem. So we are going to say we have a bunch of input. We want to be able to predict what the output is. And typically the input is represented as a vector. So here we have an input vector x, which has n components here, which x1, x2, all the way up to xn. And if you're doing a simple linear regression, then your function z is you're going to be your output. Your z is going to be some weight vector w multiplied. We're basically doing an element-wise multiplication of the weight vector w times x. Right. So that's the first step, which is the linear combination of inputs is what you're going to get. And then you're going to add another vector of size n, which is going to be your bias term. You've all probably seen this equation before when you did a very simple linear regression in 2D, right? We would write it as y equals mx plus c, where m is going to be your slope and c is your intercept. Here, if you're writing it in an n-dimensional way where x can be of n dimension, so your weight vector is also going to be n dimensional. Multiply your weight vector times x, add a bias term, which we typically call as b or w naught. So this is basically a linear regression. So you basically have your input go through a linear operation. And once you get the output of that linear operation, you put it through a nonlinear activation function. A nonlinear activation function could be something like sigmoid or tanh. I'll show you how they look like, but that's it. That's the entire single neuron. A single neuron basically is a collection of input vector. Our neuron takes in an input vector, multiplies by a weight vector, then it does a summation over those operation and add a bias term, and then you put the whole thing through a nonlinear activation function. And whatever output you get is your prediction of your neural network. It's a very, that's essentially the components of a single neuron. Okay. At this point, I'll ask if your surnames from I think L through Z. So please go ahead and make sure you can start your Jupyter notebooks now. We will, so if you have issues, please make sure to wait for about 2 minutes and then try, because you will all be hitting the system at the same time. You want to make sure that it doesn't crash us. All right. So what you see here is basically an input vector multiplied by weights and a bias term that gives you the linear combination of inputs. And then you have a nonlinear activation function, which basically makes our operation or curve fitting much better. Okay. So let's go ahead and try to build our first neural network. So what I would like you to see is keep this page, because this page has the completed out version. So in case you get stuck, this is a good page to go back to. So if you're just joining us, pasting the link one more time, go ahead and click the exercise aspect in there. So hopefully this will open up our exercise version of the perceptron. So we should be able to use our notebooks directly and do some activities in here. Okay, so like we were here. Let me go ahead and click that link. Okay, and make sure you click on the exercise, open and design save. And your solution is here. So if you ever get stuck, just keep this window open as well, so you can follow along. Okay. You should be able to now see your Jupyter Notebook opened in exercise, Python perceptron exercise. It should be under training webinar. You won't be able to save this. So if you want to save your version of it, go here, File, Save Notebook As, and then you can put it under, so this is under community data. You want to put it under my data and somewhere in my data. So this is how I would save your notebook as. So go to save notebook as, and then type in, let me go home. Okay, I'm going to do my data and then perceptron exercise. Otherwise, you will still be able to work with this, but the only thing is you won't be able to save any of the local changes you've made. So just go File, Save as Notebook, type in /my-data and the exercise notebook, and you should be good to go. All right, Design Save gives us a nice compute environment with Jupyter already installed. We'll go ahead and install some libraries, which we are going to use. In order to install libraries, we are going to use the command called pip. So pip, this is just to make sure that we have Python 3 version of pip. Install PyTorch. We are going to use PyTorch as the machine learning library today. There are multiple options like TensorFlow, Keras, and others like JAX. PyTorch is currently the most popular one, so we'll use that to build our neural networks. Okay, and then Matplotlib and NumPy. Because mine's already installed, this might run quickly for me. It might take different times for different folks. So please wait a few minutes and it will be ready. So once you install this, or once you run the command, you might have to go here and make sure you restart the kernel. This allows the kernel to reload any of the new packages you had just installed, so it will know that you went and installed something new, and that's available for your Jupyter Notebook to use. Okay, I think I've tried to delete everything, so your experience should look like mine. So this will take some time to install, as we will try to write our first code. Okay. So we have an input vector wx, and we're going to have a weight vector w, and we're going to write our first perceptron. Okay, so scroll down here, you will see import numpy as NP cell. This is where we're going to write our first ever perceptron. So here we have an input x, so you can see that. So we have an input x, and we have a weight vector w and a bias term p. Right. So all we need to do is do an element-wise multiplication, basically do a x dot w dot product, do a summation, and add the bias term. So we know here we're going to multiply 3 times -1, so -3. And then you have -2 times 2, so -4, -3, -4, that will be -7, and add a bias term b. So we're basically going to build our first perceptron, which is going to be this function. Define a perceptron, which takes 3 inputs, x, which is your input vector, your weight terms w, and a bias term b. I'm just checking. Okay. Yeah, if you click on, I think if you're not able to find the file, you will be able to just click here. That should take you to the training webinar community data. So that should open up your perceptron exercise. Okay. So let's go ahead, write our first function. So this is our first neuron which we are going to write. So this is the linear part of it. So we're going to basically do a dot product between our input vector x and your weight vector w, and add a bias term. So this is basically saying Z is equal to W times X, or more precisely, it's a dot product of W and X, and then you're going to add a bias term B. So this is just the linear part of the perceptron that we have written. So if you go ahead and make a prediction, what that Y would be, it's going to say that is -6. Let's see if we have installed everything. So it's still installing PyTorch for me. My screen's not shared?
Your screen is shared. I think people got a little behind on other things. We can't share multiple screens at once, I think, unless you copy a screenshot to the chat.
Yeah. Oh, were they asking for someone else to share? Sorry.
Yeah, everyone sees your stuff very clearly, Krishna.
Okay. All right. Thank you. So once this installation is finished, this is just installing Torch, and then we'll be able to go ahead with this. So this will basically output a value of Y equals -6. So you gave an input which is -1, output is 2. We multiplied it by a weight vector. I didn't explain like how we generated the weight vector. At the moment, that weight vector was just a random number, which was 3 and -2. And I also just chose my bias to be 1.0, right? So this model is not trained at all because we randomly initialized a weight value and a bias value. What happens in a neural network training is basically these parameters, which are your weights and biases, they get updated to make sure that the prediction it generates matches the true value you give during the training. So the goal is to, during the neural network training, what actually happens is that W and B keeps changing until the neural network is able to match what the predicted value should be. Okay, so we've only written the linear part of our work, which is the linear function Y equals WX plus B. But if let's say I want to do some classification type problem. If I'm doing a classification type problem and I have a data like this, and you can see there are red dots and green dots, and I try to divide it up with just a linear function, no matter what, I will never be able to come up with a very good model. One way to do it is maybe like I'll have multiple linear models and just segment different sections with multiple linear models. That's one way to do it. Or the other aspect of it is, why don't we take the output of our linear model? That is what we get here. This is our output of the linear model, and put it into a nonlinear activation function. That's the second part of our neuron. So the first part is basically a linear combination, and the output of the linear combination is now going to a nonlinear activation function. Okay, so which nonlinear activation function should I use? Because you can see that you need to be able to model something really complex, and most of our machine learning problems are going to be higher dimensional, which means we're going to have even more complex systems. So how do we model that? So the nonlinear activation function, there are few options. Some are like sigmoid activation function. This is a very popular one, which range where the for all your input, the output range is going to be between 0 and 1. There is also a tanh activation function, which basically looks like sigmoid, but rescaled version, and it varies from -1 to 1. So if you go ahead, run this cell, let's see if I've finished installing it. Okay, so you should be able to see like successfully installed everything, and it's still probably trying to install matplotlib and numpy. Hopefully, yes, I think we are done. Yes, once it's done, you will see a number that basically says at which point this cell was executed. Now we are all good to go. So now if I run this, you will see that my prediction was -6. Of course, we know what the prediction is because we can look at what is my weight and bias terms. All right, this model is not really useful because we have not really trained on anything, but it basically gives you an idea of like what a neuron does, or part of a neuron does, which is the linear side of things. Then we're going to get the output of the linear part and put it into a nonlinear function. And we have different nonlinear functions. So you can see that red dots, which is the sigmoid activation function, the output of your linear operation goes here in the x axis, and based on the output, we can see what will be the activation function, or the output of our activation function. It doesn't always have to be scaled between 0 to 1 or -1 to 1. You can also have functions like a ReLU, which is called a rectified linear unit. Rectified linear unit is basically saying there's no negative values, no matter what your x value is. If your x value is negative, the output is basically 0. Only if you have like positive x values, you're going to have positive y values. This will be our prediction. One of the things we're going to learn is how to update the weights and biases. And if you look here, some of the slopes of these functions, like here, it flattens out. So if your input is too large, you might not be able to update your weights and biases. So this is what we will call as exploding gradient problems or vanishing gradient problems, because your gradient basically goes to infinity at these points. All right. So we have these linear functions. Now we have nonlinear activation function. A perceptron will only give you one output, but sometimes we need more than one output. So what do? We string together multiple perceptrons to create a neural network. So we've written a single neuron, which was Z equals a nonlinear activation function, which takes the input of the linear output. Now we are basically going to combine multiple of those nonlinear activation function and linear output neurons into a single layer neural network. A neural network is basically a collection of multiple neurons. Okay, so this x1, x2, x3 is your input vector. W1, W2, W3 is an output. We use your weight vector. We multiply this, add a bias, get an output with a nonlinear activation function. This is the single neuron. You can stack multiple neurons like these together, all taking in the same inputs, and they all generate an output. And you can use those output to collect them together to get your final output. So the layer you see here is what we would call as a hidden layer inside our neural network. Okay, so there's the input layer, there's a hidden layer. You can also stack multiple hidden layers and collect them together to generate an output. Okay, so this is how a neural network would function: is take inputs, have weights, and you can see the deeper, the more inputs you have and the more weights you have, your layer is going to become really large, and you can have multiple layers of these to create a deep neural network. A deep neural network is basically a repetition of this network and create multiple layers of them. Okay, so we produced an output which was -6, right? So if we scroll up, you can see that the prediction is -6, but we have no training. We didn't actually tell the neural network how should it make the prediction. We just randomly initialized a weight and bias and say make a prediction. So this is just a random output. It has no meaning. So now we want to be able to train the neural network or any of these neural networks with a given output. So how the neural network generally works is you have a bunch of input vectors, which are x, and you're trying to predict what is your output, which is y. You also have in this case, this is the prediction. So we are going to call it y hat. I'm trying to write here, y hat prediction. You also have a collection of true x values and true y values as well. So you have these actual y values which you have observed, and you want to train a neural network so that it can predict what the y value should be. And by training, we're basically saying, I want you to train what are my weights in different layers and biases in different layers, and make sure you update them so that when I give it an x value, I multiply by weight plus bias, sum and activation function, I'm able to make a prediction y hat that is pretty close to my true value. Of course, if you already have xt and yt, you don't need it, but you're trying to make predictions on values which you don't know, right? So how do we define y prediction and y true, and how can we update weight and biases? That's going to be our next step. How do we update weight and biases? Okay. So let me close this here. Sorry. Okay. There we go. All right, so now we're going to train our neural network. By training, we're basically going to evaluate what the prediction will be and then compute a loss. Loss is going to be the difference between, typically we're going to define the loss as the mean squared loss. So we're going to define loss term as L. And the mean squared loss is going to be your y hat, which is the prediction of your neural network, minus your y true value, and you square this value. This tells us how bad our prediction from our neural network is. So if your neural network prediction is completely off or bonkers compared to your true value, then you have a huge loss. If you're able to minimize this loss, then your neural network has learned from the data. So that's what we are going to do is, how do I minimize this loss value? And whenever we say minimize, it basically means we're going to compute the gradient of the loss with respect to the weight, and gradient of the loss with respect to the bias term. And we have to do it for each layer. Okay, so that's our task right now. Sorry, it switches between my iPad and here. Let me close this. All right. So we need to first calculate the gradient, and the gradients in neural network is calculated to something called backpropagation. I don't want to go into how this gradient is calculated. That will be an entire lecture. Instead, we want to look at how are we going to use these gradients to find out the lowest loss point. And we typically use an algorithm called stochastic gradient descent that works this way. So we evaluate what is the loss, and here the loss is shown as J. And we start off there, and we want to go to the minimum point. That basically means I want to minimize the error between the prediction and the true value. And each point, you're going to calculate the gradient of the loss with respect to the weights, gradient of the loss with respect to biases, and update it using a stochastic gradient descent algorithm. So this is called the weight term W. There's a learning rate. We don't just take the weight and update it. We multiply by a small factor, typically like 1e minus 3, 1e minus 4, of the gradient of your loss function with respect to your weights and biases. And this allows us to update the weights and biases iteratively. Okay, so this is how the code would look like. So we're doing a training loop. And here we basically have epochs, which is basically 1,000. An epoch is defined as going through your entire training data set once. So if I'm saying epoch is 1,000, I'm saying that I'm going to go through the entire training data. Those are, remember, those are your true value, y true, 1,000 times, and compute what is the loss, okay, at each of those 1,000 times. So for each of those 1,000 times, you're going to make a prediction with your neural network model, taking X as the inputs, weights and biases as the training variable. Use that to make a prediction, and then you compute the mean squared error. That's our loss. So once you compute the mean squared error, you're going to compute the gradient of that loss. Here I'm just like manually computing what the gradient is, and then go ahead, update my weights and biases using this equation. So this algorithm is called gradient descent. It's called stochastic gradient descent because we don't sample every weight and biases, instead do it at a smaller subset of sample. But basically, we take the weights, use a learning rate. Here we use a learning rate of 0.1 and update the loss and the bias terms. Okay. So let's go ahead and write our first neural network. Okay, I'm going to do a simple problem, which is, let me clear this drawing, is doing a cantilever beam. I have a point load at the end of the free end of the cantilever beam. We know the deflection at any point along the length of the cantilever is given by this equation here. where P is the load, X is any position from the fixed end. EI is your modulus of rigidity, so Young's modulus times moment of inertia. And we can analytically write that equation, right? So along the length of the beam, I have a 5-meter long beam, and we are going to estimate what is the true value here. So go ahead and run this cell. So we are also adding a little bit of noise, which is basically me saying there's some amount of noise in my measurement of my deflection values, right? So here, let me go add a cell, and let's try to plot this. You're going to do matplotlib dot pyplot as PLT, and we are going to plot your X versus your true value, right? So let's see what it, did I not import? Let's look at, I forgot lib. I said lib, I didn't. Pyplot plt.plot. Okay, there we go. All right, so is this big enough? Can you, hopefully you can see what I'm typing here. Is import matplotlib dot pyplot as PLT, and go ahead, plot it. You can see for those 5 meters, this will be the true deflection value. Of course, this is the analytical equation, so you expect to get that true deflection value, right? Now what we are going to do is take this true deflection and pretend that we are going to make measurements, and because we are making physical measurement, there is some amount of noise in that measurement. So we're going to take the true value of Y deflections, and I'm going to, so maybe do a scatter plot so you can see how this looks like. And I'm going to take the true values, add a little bit of random noise to that, and see how that would look like. So plt.scatter, again, X now with Y noisy values. All right. So you can now see that I've added a little bit of noise in my measurements. Those are my orange points. The true value is your analytical expression, but we are going to use just the noisy data to train a neural network. So we want the neural network to use this noisy data and understand how a deflection of a beam actually works. Okay. So is the problem clear? The problem is take this simple one-dimensional data. So given a lot of X, you want to predict what is the deflection. That's the goal of our neural network. And we are going to use this neural network, train it, and then see if we can predict it. So we will understand all the process. So the first step is we already have the true data. This is the data on which we are going to train. So if you want to look at how that data looks like, so we can go ahead and print out X. So X is a tensor. And if you're familiar with just NumPy, we're just going to use PyTorch. So make sure you import Torch, import NumPy. We set a random seed. This is just to make sure that my output looks reasonably close to your output, not completely different, that your output looks way different from what I'm trying to do. Okay. So all these 4 lines is basically trying to make sure that your output, which you're running in your system, is same as my outputs. The reason why we want to do this is our weights and biases are going to be initialized slightly differently. And we want to make sure that the weights and biases are initialized randomly, and then we will iterate until we get to a convergence. Okay. So we have a PyTorch vector. So in order to create a torch vector X, this is the same command in NumPy, numpy.linspace. We are going to use torch.linspace. And we want all the vectors, input and output, to be torch vectors so we can actually differentiate through them. Okay. So here's going to be our first parameter. The first parameter is going to have 16 features. So like in order to give you an idea, let's go look at one of our neural network here. So this neural network has 4 features or 4 parameters, and this is a single layer neural network. If you were to create a 5-layer neural network, then it basically means you will have one more layer here, one more layer here. So it depends on how people count. Sometimes people call this a 3-layer neural network because there's an input layer, a hidden layer, and an output layer. But some people prefer to call number of layers just based on number of hidden layers. So don't get too confused about it. Just ask whether it's just they're referring to number of hidden layers, or are they including the input and output layer. So I can call this a 5-layer neural network if I say there are 3 hidden layers. So these are the 3 hidden layers. And then there is 3 hidden layers plus 2, 1 for input, 1 for output. Okay. So we are going to create a neural network. Let me see. I'm going to actually create a neural network which takes an input and a hidden layer and 3 hidden layers. Let's do this one. Okay. So let's go ahead and define a model. The first step is to define a model, and then we're going to use the torch.neural network NN, torch.nn.sequential. So make sure that you capitalize sequential. If at any point you feel lost or you can't copy the code, the solutions are here. So you will be able to go to the neural network example and copy the corresponding code from here. So if you're lost or you just want to follow along, just use the book. And if you want to just type out with me, then feel free to do that alongside. Okay, the first is going to be a linear layer. So previously we wrote it by hand. Now we don't need that. We can actually just use PyTorch and ask for a linear system. Now, whenever we say linear system, we are doing WX plus B, right? And the linear system is going to take 1 input. And in this case, position is going to be the input. And we are going to have it produce a 16-feature output. So the linear layer takes 1 input and it converts it to 16 outputs. Okay. Then you're going to pass this on to a nonlinear activation function, which is tanh. So remember, tanh goes from -1 to 1 in terms of the output. So whatever the output is, your output is always going to be between -1 to 1 for this. So this is going to be 1 layer. So it's a linear layer plus a nonlinear activation function. So let's go and add another hidden layer. So we will do torch.linear again. And the output should match, the input of this layer should match the output of the previous layer. So if you had 16 before, make sure your input is now also 16. Okay. And then this is also going to produce a 16-feature output. Pass it along to a tanh activation function. And then we will now create an output layer. So this is our input layer. This gets the input. So the input goes into 1. So the input is 1, which is the position. And then it outputs a 16-dimensional hidden feature. Right. And then it goes into so that's the linear part. And this is the nonlinear activation function. Then you again have a linear layer. Then you have a nonlinear activation function. Then finally, you're going to output a linear layer, which takes 16 inputs from this output and produces a single output, which is going to be our Y deflection, right? The deflection of our beam. So that's it. So we have defined our first model. Congratulations. Let's go ahead and output this, and you will see that the model has now 5 layers: the linear layer, an activation function, a linear layer, activation function, and a linear layer that produces an output.
Krishna, we have a question though in the chat.
Yeah.
How can we take the noise value from the true value? Is there any ranges?
Noise value, thanks, Tracy. Noise value, we are just adding so that, like typically if you're making measurements, you will already have noise in your measurements. I'm just simulating that our measurements have a little bit of noise. So if you change this value and make it like larger, you can see that it will be completely wrong. So there's going to be no trend. And if you basically have no noise, then if you look here, then it will recover back the analytical equation. Because I'm just synthetically generating the data here, I'm going to add a little bit of noise to say that this is not a perfect relationship. I want you to learn from the data. Okay, so we should have a model defined. Now, the next step is if you go ahead and look at the weights and biases in here, they will not be, they will all be initialized randomly. So we can't just use the model now. Well, technically we can. So why don't we try to do this? So let's go ahead and make Y predictions. So we have a model, right? And then give it a list of X values, and then try to plot how this looks like. Okay. So let me go ahead and do plt.plot for all values of X and your Y predictions. So maybe I'll detach it here. So Torch is going to compute it, and we want to convert the Torch vector to a NumPy vector so we can actually plot. If you do this, you can see that this is the deflection that is learned. What is the true value? That will be interesting to plot, like whatever measurements we had, X, comma, Y, no, what was my Y noisy? Okay, noisy. Okay, this is what I was expecting the model to learn. I should probably do scatter plot. This is what I was expecting the model to learn, the scattered data, and it ended up learning a model that looks like this. So the blue dots are what the model thinks it should be. The actual result is here. Of course, we haven't trained the model, so it is going to generate something completely incorrect. So this is totally valid at this point. Okay. Now we are going to go ahead and train the model. And you know what to do to train the model. So the first step we are going to do is make a prediction from the model. So we are going to take all the inputs, and we are going to go through the entire input data 1,500 times. So we are going to take all the input data and train it 1,500 times. Typically, if you're doing machine learning, you will split it into training and validation. That's not the main thing for today. So I'm trying not to split it and use the entire training data and predict somewhere else, which is not in my training data. Okay. Okay, I think, Jose, that's a great question of like what activation function you would want to choose. Typically, if you're doing an engineering problem, at least choose a hidden layer activation function to be tanh. So if you go back, look at the tanh activation functions, they all have positive and negative values. If you use Sigmoid, you're only going to get positive values output. And remember, tanh can only output between -1 to 1. It can give you no other output. So if you want an output that is positive and negative, tanh is a good one, but it will limit your outputs to -1 to 1. If you want values outside of the range, the only option is rectified linear units, which is basically saying no outputs when your input is negative and positive values of outputs. If none of those work because your deflection could be positive or negative, use something like I've done where I use a linear layer at the end. Where is that? Yeah, linear layer at the end here. Typically, your activation function is going to be tanh when you're doing you don't have to normalize because tanh will convert the output to be -1 to 1. Okay, but tanh is a good activation function for most scientific problems. All right. Okay, so the first step is make a prediction. And then next we need to evaluate a loss. Loss is going to be mean squared error loss. That's what I've defined here. We have defined a criteria. So you can just do a criterion is your Y prediction, comma, the noisy data set. But I'm going to add an extra term to just make things. This is batch normalization, or this is for doing it in batches. So instead of taking the entire data set and doing it serially, it'll just split it into batch and do it. That's what the unsqueeze, not squeeze, unsqueeze is trying to do. All
Krishna,
right. And
Krishna, there's a question about, are we not supposed to normalize the inputs?
I answered it verbally.
Okay,
no, we don't need it
Okay,
because Canh will always output between -1 to 1. Thanks, Chris. All right. So we have the loss. Now we are going to reset the optimizer because it's in a loop. We want to make sure that our optimizer is reset or zero the gradients in the optimizer at the start of each step. Calculate the gradient, and we're going to calculate the gradient by calling the function called loss.backward. This is the reverse mode automatic differentiation that happens that gives you the gradient of your loss. Remember the dou L over dou W or dou L over dou B. That's the term this calculates. And we move the optimizer to the next step, which means it can adaptively learn learning rates. Okay. That's it. You have now written your first training loop. It is basically make a forward pass, make a prediction, compute the loss. How does your prediction compare to your loss? Take the mean squared error, calculate the gradient of that mean squared error, and make sure you update your weights and biases. So like here, we calculate the gradients. And then this is where the weights get updated by like eta times dl over dw. And bias gets updated over using the same equation too. I'll remind me again, I'll talk about the GPU stuff after I finish this notebook. Okay. We have GPU instances as well, which are Frontera RTX nodes. Design safe is free, and also there's a huge amount of data set that's available. So if you're using Colab, you basically don't have access to those data sets, in which case you would have to download all the data set, try to do analysis. Here you have the entire workflow potentially inside your Jupyter notebooks. I have access to all the published data sets on Design Safe. You can just go here, near published, and look at that. So yeah, thanks, Kayla. So let's go ahead and train it. So we're going to run this part. So it's going through 1,500 times and plotting the error every 500 steps. You might get slightly different results as you train, and you can see that the model does reasonably well. So it has fitted a model, and it has a small error, but it does pretty well. If you look at the loss between what it predicts and what the true value is, that loss is pretty small. Again, that because your deflection values are also small. They are already in 1e minus 2, 1e minus 3. So your loss, when you square it, it's going to be even smaller. So what you see is a deflection of a cantilever beam. And this is an open question, so whoever answers fast on chat. In the model's output, remember this is a cantilever beam, so the fixed end is at 0 and the free end is at 5. Do you notice something weird about this output in terms of deflection? Do you see something strange? Well, I'm asking especially in the orange line that it has produced. If you're saying that this is the fixed end, right? At x equals 0, it should be a fixed end. At x equals 0, you can see that it doesn't give you a 0 deflection. It basically gives you a non-zero deflection, which is not right, which is not what you would expect. But the model, the neural network, had no idea that you are modeling a cantilever beam. At no point did you tell the neural network, this is a cantilever beam behaves this way. So make sure you understand what the expected behavior is and make sure you put those physical rules in it. And this is where having that engineering background actually helps, because if you're just purely a data scientist or a machine learning person training the model, you will see that your loss is 1e minus 7, which typically is a pretty good loss. And you can see like over the entire profile, it models very well. And probably you don't know what the true deflection is, right? If you do know what a true deflection is, you're not going to train a neural network. So you're basically dealing with a bunch of data. Then you will say, oh, this model actually fits my data really well. My orange line is closer to the blue dots I have here. So I'm happy with this. But once you have your engineering knowledge, you can say, I should have zero deflection. I shouldn't have any slope at that point. So that's where we want to make sure that we can put some physics into our neural network. Hey, I come to my topic of physics-informed machine learning. So how are we going to put physics into our machine learning model? The place we can put it easily is to say that we have this constraint that at the fixed end, that is at x equals 0, we want to make sure that the model learns the deflection should be 0, right? That's the physics we want to put in. So why don't we go ahead and put that into our model? So instead of just using the mean squared error as the loss, we're going to go ahead and change our loss and by putting a little bit of additional physics into our model. Okay. Makes sense, right? We're basically going to constrain our add boundary condition that says when you're computing the loss or minimizing what the fit is, make sure that you apply that constraint that at x equals 0, you should get 0 deflection. Okay, so we're going to do that by modifying the loss function. So we have like this physics-based loss function, and which takes y prediction and y noisy, which is our true value. Let's just call it y true, and compute our. This is the training data from y, right? So let's call it y data. So instead of using the criteria, which is the mean squared error, passing y noisy value and y prediction, we're basically going to rewrite our loss function. The way we are going to rewrite the loss function is first make the prediction, y prediction, and do squeeze. Again, this is just if you're doing like batch way of doing it. Batch is like chunking large amount of data together and do it in chunks. And then we have the y data, and make sure you squeeze your y data as well. Okay, so a data loss is what we would have typically done, right? Is this. So we can define a variable called data loss and say we are going to calculate the mean squared error, torch.mean, and it's going to be your y prediction value minus your y data value, and you're squaring that, right? So this used to be the original criteria. We have not changed that. This is exactly the same method before, which is data loss is the mean squared error loss between your prediction and your actual data. Okay. Right, so if I return this and then run this model will look exactly same as the previous one. Nothing else changes. We haven't actually applied a constraint. Okay, how do we incorporate physics? The way we incorporate physics is add an additional term to it. Let's call this as boundary condition loss, because most of you said it's a boundary condition issue. So let's call it a boundary loss. Okay, so we are going to define a physics-based, in this case, engineering-based boundary loss, which is to say that the deflection should be 0 at the boundary. We can define that as boundary loss is, again, a mean squared error, but it's going to be a mean squared error between the predicted value. And in this case, we usually give the prediction at x equals 0. And you subtract it from the 0th value and square it. So this gives us the mean squared error at the boundary. This is equivalent to me setting like y prediction at x equals 0 should be 0, right? That's what I'm trying to do, or saying like minimize this as the loss. And then we say the total loss is going to be data loss plus boundary loss. And because we have like only one boundary condition, And whereas this data loss is going to be on 1,000 points, I think that was 100,000 points across. We want to make sure that the boundary loss is emphasized. And we can do an emphasis by adding a weight. And this could be a weight vector of 10. So let's define alpha, which is like a weight, to how much weightage should I give to this boundary loss term, right? So you can play around with this, but just use a weight term of 10 so that we are emphasizing really that make sure the boundary is constrained to 0. So the bigger the number, the more weightage it is giving to the boundary loss compared to the data loss. Again, if you ask me what this value should be, the way I would do it is look at what the data loss is, then print out what the boundary loss is, and make sure they are roughly in the same units to give equal emphasis. So the order of the data loss should match the order of the boundary loss. That's the goal. Okay. So now we've defined all this. We can go ahead, run this. This should take like just a few seconds to run, and you can see how loss was initially 1 minus 3 and start to decrease, and we're pretty stable. So this seems okay. And let's go ahead and plot the results. And hopefully, if we did everything right, we got that constraint pretty solidly that at x equals 0, you make sure that the deflection is 0. So we've forced the model, added some physics in it. So this was our first step. And we say that our prediction value will make sure that it is 0. Okay, I'm going to look at the question. Yeah, in this case, the data has to be prearranged to be fixed at y prediction 0 needs to be the fixed end. But I'll do a more general example. This was a simple example for you to do, like how to get used to it. And then as we do the second example today, and maybe in the future, when we do part 2, I'll give you a more specific way to do boundary conditions. And we can say at x equals 0, make sure this condition is satisfied. We can do those. But for now, this is just a toy example so that you understand what's happening. Okay. All right. So one of the things I would recommend doing is go change the loss, go change the learning rate, see how quickly it learns, change the amount of data set, because all of those is going to control your results. So that's something you want to try tuning it, but you've done your first physics-informed machine learning model that gives a reasonably good output, but also make sure that that constraint is valid. That is, at fixed end, you get 0 deflection. I want you to remember this is what we would call like the soft constraint. This is not a hard restraint. We're basically asking, if you may please make sure that at fixed end, the deflection is 0. We are not forcing it. This is not a hard constraint. This is the soft constraint that asking the neural network to please learn that at x equals 0, this is fixed end, that you get 0 deflection. It doesn't guarantee a 0 deflection. If I run this multiple points, I might get a non-zero deflection, but I think my weight is large enough that I need to train. I can't just keep running the same thing again. If I do a different training model, so I get a different model now, because every time things get initialized differently, it's still going towards 0, but it is not exactly 0 like the model we had before. And when you do get lost like these, it basically means your learning rate or your optimizer is not the best. Again, it's a tie problem, so I'm not focusing on that too much, but this is something you want to try and avoid and make sure you have your loss degrading pretty smoothly. So when you make predictions, it's pretty reasonable. Okay. And why did it change? Because every time the model weights and biases are initialized randomly, so you have different outputs. Okay. But if you train long enough, we are only training like 1,500 steps, but if you train long enough, use the correct optimizers, then your results will, of course, improve and will remain stable and won't change significantly as I just retrain the model. Okay. All right, that was example 1. We are only going to do 2 examples today, and the other 2, you can look at it, or we'll do a part 2 of this physics-informed machine learning course. Okay. Right. Any questions so far? you could do physical constraints like this, but then that you can always set at x equals 0, you get the output, like get the output from the model and then add a constraint. But you will see that that's only applicable if you have boundary conditions. If you have like differential equation describing your system, then you can't do that. So again, use that as a toy example, but let's do part 2. So go ahead and click the exercise, sorry, not part 2, second example of today's webinar. Go ahead and click on the PINN exercise problem. Okay, so what we're going to do now is basically do a 2D example. So we are going closer to more a real world example, and then try to do it purely data-driven approach. And then I'll try to show you how you're going to incorporate the loss function. Yes, we can. You can train it on any finite element type data. Like I'm in part 2 of this physics-informed machine learning, I'll show you how to train a heat transfer problem. Burger's equation, you can do it on finite element data or CFD type data. It doesn't matter which PDE you're going to solve. So I'll show you a PDE example now. That's what we're going to do. All right. So make sure we have, this is just to plot something. It's not going to take as much time as before. So again, this is the second exercise. So we were here, go to physics-informed neural network. If you just want to follow along, just scroll through. If you want to try out the exercise, click on this, open in design safe, and make sure that you save it locally if you want to keep your changes. I have this version, so I'm not going to, maybe I'll do it just so you see where I save it. So you're going to put it under my data, name of your file, and anything you don't put in my data will be erased. So make sure you have everything under my data. Okay. All right. So I guess I need to open the my data version. So let's go ahead and exercise. This is the my data version. Okay. Install the libraries. That went very quickly. So we're going to now generate X and Y data. And then we're going to train a neural network that produces a output like this. So we have a mesh grid of X values and Y values. Okay, and this is going to be our training data, and we are going to use a neural network to be able to train on this data and produce this output. And then we are going to use a physics-informed machine learning approach to incorporate a PDE equation that describes this data and see how that performance will improve. Okay, so the first step, before I go, I'll quickly say what the universal approximation theorem is. Universal approximation theorem basically says as long as you have a neural network, you will be able to approximate any continuous function. This doesn't say like how deep a neural network you should be, how many parameters or features you need to have in a single layer. It just says using a single feed-forward network, you will be able to approximate any continuous function. And that's also good because you need to be able to differentiate to calculate the loss with respect to weights and biases. Deep neural network are exactly the same as what we've done. The only difference is you're going to have multiple layers. Here we'll see, like, as you go to a bigger problem, how our neural network complexity will increase. So you should be able to generate this training data set. Let's now go ahead and create our first neural network. Previously, we had an easy way to do it. We just did model equals and then defined everything. That's one way to do it. But as you start to build more and more complex model, you might want to build your own class in PyTorch. So this is a standard neural network I'm going to define, which basically inherits my object from the PyTorch neural network module. So here, if you're going to define layers, which basically is the neural network model. So you have a sequential model. Make sure you open and close parentheses. And then I'm going to define 3 linear layers with activation function and an output layer. Okay, so we're going to define a linear layer. What is the input to the linear layer? The input is given an x and a y. I need to be able to predict what is the output z. So the input is going to be 2 features. So you can be explicit and say input features is going to be 2. So that's my x and y coordinates. And then I'm going to write to a feature set of 10. So I have 10 features in my first hidden layer. Then I'm going to have a nonlinear activation function, right? Then we're going to repeat. So I'm going to have, I said I will have like 3 linear layers. So we'll repeat the linear layers. You don't have to, I'm lazy, so I'm not going to type in features equals 10, out features equal to 10. We need to make sure that input features and output features match. So you can just do 10, 10, followed by an activation function. Then let's do another linear layer, which is 10 by 10. And then we are going to have another activation function. Then finally, we will define an output layer, which takes the hidden dimension of 10 and then outputs a single value, which will be whatever the output is shown in red or blue here. Okay, so we've done this. And the reason why we are doing this instead of just saying model equals torch.sequential is so that we can concatenate the x and y inputs here. So this is the forward pass. Forward pass is basically what we say as the prediction, not loop, it's the prediction function. So we're going to take our x and y input as 2 separate inputs into a single array of x, y. So we are going to concatenate x and y together, so x comma y, and we are going to concatenate, which basically means like append array one to the other into a 2D array, and we are concatenating it in dimension 1, basically concatenate columns. If you concatenate rows, it will be like this. Concatenate columns means you will get an output like those, right? And it is going to take the XY input and then evaluate what the prediction will be. A forward pass is basically means take the input, run it through our machine learning model, and produce an output. And that is going to be self.layers XY, which is our output. Okay, that's it. We have defined our custom class PyTorch module, so nothing super complicated. We define whatever name you want. Here we are calling it the standard neural network. Define 1, 2, 3, 4 layer neural network, input layer, 2 hidden layers, and an output layer. So this is basically your input layer, and this is your hidden layer number 1. And this is your hidden layer number 2. It's hidden because it's not visible to the input or the output. Then you have the output layer, and there's activation function after each of those. Okay, now we will go ahead, define the model, and it's just the instantiation of the class object. Go ahead, print out the model, and make sure that you have all the layers. So we had 1, 2, 3, 4 linear layers, 3 activation functions. Everything's looking good. So now we define same thing as before. So this is exactly the same method we've done before. So we are going to define a criterion, which is the mean squared error loss, MSE loss. And we're going to use an optimizer. So previously, we used a stochastic gradient descent optimizer. Here we are going to use an Adam optimizer. It is an adaptive momentum-based optimizer. And then you need to say which parameters are updated. So weights and biases of the model is being updated with a learning rate of 0.01. So you can also use stochastic gradient descent, which will look like this, SGD. Or you can just use the Adam optimizer. So the gradient which are computed through the backward pass will be passed to Adam, and Adam will be able to update weights and biases. So your prediction will change as your training loop changes. So for epoch in TQDM, we're going to do, you can just do range, but we're going to put it in TQDM because that gives us a nice like progress bar, right? Here we're going to go through it 5,000 times. So we're taking the entire data set, going through the data set 5,000 times. That's one epoch is going through the entire data set once. We're going through that 5,000 times. So initial step is making sure that you zero your gradient. Then make your prediction, which is take your model, give it the X data and the Y data, make a prediction. What do you do after you make a prediction? You compute your loss. And loss is basically this function, which is the mean squared error loss between your prediction and your data value. Right? Then once you have a loss, calculate the gradient of your loss with respect to your weights and biases, which is loss.backward. And then once you have your gradient, you want to make sure that your gradients updates your weights and biases, right? This is initialization. Sorry, there's a typo. This is predict with your model's weight and biases. And then here, evaluate the loss, which is difference between like your Y prediction and true value, and then make sure you square it. And then here, calculate the gradient, which is DL over DW and DL over D bias, right? And this is the step where update, so the weight gets updated as eta times DL over DW, right? Bias will also get updated the same way. Okay, and do I plot the training loss? Okay, I need to plot the training loss. So let's create an empty array. And each step I'm going to figure out what is the loss, and append it to the empty array, right? Loss.item. Okay, so now if you run it, you will get a nice progress bar, and it tells you how long it takes to. It runs 300 iterations per second, so it runs through 5,000 epochs very quickly, and it's going to plot the training loss versus epochs. All right, again, like I said, high learning rate, but I want to run this example quickly, not spend too much time, so we're using a higher learning rate to get to a solution quicker. Now, we have all of those things put together here. Now we can, that's all, nothing changes. I'm not skipping through anything. Let's go ahead and test how well our model works, okay? So if you go plot the model, the left-hand side is our original data set, and the right-hand side is what we get from the trained model. So that's pretty good, right? So you're able to compare the true value and predictions, and we are doing well. And you can also, I think this is already installed. You can also go ahead and plot the error. So the difference between might be, okay, I was trying to do an error in 3D. I shouldn't. Let's look at how good it is when you try to extrapolate. Okay, so let's go ahead and copy the test the derivative-driven model. So copy this, please. And we are going to now test it by extrapolating the range, okay? So we trained it on -pi to pi. We are now asking it to predict in the range of -2 pi to pi, okay? And if I ask it to predict it, now you can see where the training data set was. Like the training data set was between -pi to pi. The prediction is pretty good, but it's all blue here. It hasn't learned that the Z changes based on, Z has a periodic output range. It just assumes everything is blue or everything is red in these regions. So how can we improve this particular model? This again goes to our topic of physics-informed machine learning. Can we bring in physics? So if you want, please read the original paper from Ray. And that's the physics-informed deep learning, where they're going to add a physics-based loss function. So previously, our physics-based loss function was just a boundary condition. Now we're going to do something better and basically incorporate a partial differential equation. Okay. So what is this PDE that governs the output? So the way we generated the output was we say the function xy is sin x times sine y, which is actually the solution to this partial differential equation. So if you take the partial differential, the Laplacian operation of dou f of the second order PDE plus 2f, then the solution is sine x times sine y. So if I define f as sine x times sine y, put it in this Laplacian operator, you can see that I will recover back the original PDE that is governing this solution. Okay, so I know this is the PDE. How do I use this PDE in my loss function? And previously, we had a very simple loss function, which was basically my output, which is f, right? My output is always f here. And my output at x equals 0 should be 0. That was easy to enforce because I didn't have any derivatives or anything strange like that. Whereas now I have a derivative. So how do I calculate derivative of an output? Of course, we calculated the derivative of the loss with respect to weights and biases pretty easily. We just said loss.backward. But what if I want to calculate the gradient or partial derivatives with respect to f, with respect to x and y? So this is where PyTorch is really useful. You can go ahead, import torch. Let's write a simple x value. So torch.tensor. And then we are going to define x is equal to 3, right? So it's just a scalar value at x equals 3. And we're going to evaluate this function f of x is equal to x squared at x equals 3. And one thing you want to do is make sure you add this value saying requires gradient is equal to true. So that says to PyTorch that we are going to calculate derivatives of this function and make sure you track how x changes. All right. So let's go ahead and define the function f. Function f is defined as x squared, and we want to be able to calculate f dash of x. What is f dash of x? F dash of x is basically 2x, and at x equals 3, it is 2 times x, 2 times 3, which is equal to 6. So let's see how to calculate the derivative of a function at a specific value. So we want to calculate f dash of x, okay, or df over dx. So we're going to use torch.autograd. That's the function that's available, and that allows you to calculate the gradient of the function with respect to the input value. So we calculate df over dx, and this basically, if you just print out df over dx, it is going to give you a tensor. Instead, if you want a number, exact number, then you can output it like this. So it will tell you what is the gradient. Okay. So you can also take the gradient with respect to x or y. Remember, our input is x, y concatenated together. So x0 will give me gradient with respect to x, and x1 will give me gradient with respect to y. So this is the first gradient. What happens if I want to calculate the second derivative? What is the second derivative of this function? The first derivative is 2x. The second derivative is constant. So you could basically take f of x and calculate df over d squared f over dx squared. Right. So torch.autograd take the function df of x, and again at x, and then print it out. So let's go print out df double x. So it's the second derivative. So when we did this, we encountered a problem. We encountered a problem because we haven't said this function is also differentiable. So in order to make functions differentiable, you need to make sure to add a line called create graph, and that allows you to differentiate through the function. So make sure you do create graph equals true, and then now you can differentiate it with respect to that function. Okay. So now we want to be able to incorporate our loss function into loss function as this. Where's my loss function? Our loss function needs to be a physics-based loss function. So this is our physics-based loss function. So I need to define everything as a PDE. Because of time, I'm going to just, let me just open this solution to show you how it looks like and how I would do it. So give me one moment, and let's run through this. It's already installed, so it should go through pretty quickly. So yeah, it is running, and we are training now, right? This is just a data-driven model. Then we show the test. And this is how like the error when the original value looked like. So we are just plotting the error. Then we will test outside the training range. Now we get to defining the physics-informed loss function. So the physics-informed loss function is basically a combination of your, let me see where that here is, output of your neural network plus a PDE-based loss. So the PDE-based loss is what we are going to use as gradients. So we are going to define the PINN class. So this part is exactly the same as before. Now we need to define the data loss, which is here, mean squared error of your F minus your original data. This is your data loss. So let me show this here. As the data loss is same as before, there's nothing new, which is basically y prediction minus your y true value, and then take a mean square error of that. Okay. And then the only thing we need to do is now we need to incorporate the PDE loss. And we know this is the system that describes our partial differential equation. And that is your dou squared f over dou x squared plus dou squared f over dou y squared plus 2f equals 0. So that's the PDE that we need to be able to define, right? So what we're going to do is calculate the function. The function is pretty straightforward, which is evaluate whatever the neural network output is, which is f equals self.forward. Forward basically takes your x and y, concatenates it, put it through all the neural network, get the prediction. So this is our prediction. Take the derivative of the prediction with respect to x, that is f.sum. We need a scalar value, that's why we do use sum with respect to x. So this is the gradient df over dx. Right? Then you take the derivative of that, which is d squared f over dx squared. You do the same again for y term. So again, autograd.grad f with respect to y, gradient with respect to y squared. Then add those two plus the 2f term. So now you have a PDE loss. Then you have your data loss. Add them together. If you want a weighting factor, you can do it. But typically, let's keep this same. That is, we are giving equal weight to the data loss and the PDE loss. Okay, so now we have everything. So you basically run this. And one thing you're going to notice is it's going to be slower than just doing data loss, because now you're doing extra computing to make sure that whatever the neural network is learning is also a valid PDE solution. And we've defined what that PDE is by describing it in terms of gradients, added it as a loss term. Again, it's a soft constraint. It doesn't mean it will strictly enforce it. We are encouraging the PDE, encouraging the model to make sure that the solutions it is generating is consistent or valid. Okay. So again, I made the learning rate large enough so our losses will fluctuate. In reality, you want to make sure that you are able to do it. So avoid these little fluctuations. You will be able to tune it. Then we can test our model. The results will be better. But our big question is always extrapolation. Like, how did we do it in extrapolation? Here, we are better. Like, this is still a big problem in machine learning is extrapolating outside your training range. But by giving a PDE, our solution looks a lot closer to what the reality looks like, but it doesn't solve all our problems. So the PDE basically means your solution that the neural network learns, that is the weights and biases it learns and the output it produces, will constrain it to be PDE compliant. Don't always expect it. It will try to do it for you. So the limitations is it will take longer to compute because you're adding extra bit of complexity into your loss term. You need to have your own weight of how much PDE loss versus data loss you're going to have. But it also means extrapolating is still an issue. So something that you need to be careful about. Okay. Sorry, I went through the last part quickly, but the gradient part, the PDE loss is exactly the same as what we did before. The only interesting part is how you define the partial differential equation. And we can use this PDE by defining the gradients here. So you have the completed notebooks, so go look through those. And then I'll probably see you in part 2 at some point where we announce it to go and look at more inverse problems. I know there are some questions. I'm going to keep this feedback form open so that if you're still here, please complete that feedback as I try to answer your questions.
Also a hand raised, Krishna. So there's
okay,
a question.
yeah. Yeah, do you want to unmute and ask?
Sure. Are you all talking to me? Sorry, I just wrote some questions.
We can hear you.
Okay. So thank you very much for the presentation. I just started on this, so this was very helpful. My name is Agamanukta from the UMass Amherst. A few questions I had was when you compute the gradient, I'm assuming that is numerical, or is that
no? Automatic differentiation means it's somewhere between, it's as fast as a numerical gradient, but automatic differentiation gives you exact gradients. So this is not numerical, it's not finite difference. It uses something called directed acyclic graph. So it basically constructs the entire operation as a graph, and it will differentiate through the graph. So your derivatives are exact when you're using autograd.grad.
Okay. Two more.
I can read and answer that. So is there a way to have training points separately for data loss and PDE loss? So yes, so I'll show that more in part 2 where like, for example, a boundary condition, you will generate points only along the boundaries and do that. So we will see that in part 2 of this series of physics and from neural network, where how we could use specific points at specific locations to define different parts of your loss functions. Any suggestion for normalization of these equations? Train better with normalize, but we have PDE. You don't need to normalize these aspects. So you can put in the whole PDEs to train. So that's the benefit. So you're no longer required to normalize. So yeah, the jumpiness you saw or the oscillations you saw in the loss, because you're modeling physical systems and with high learning rates, ideally I would do a smaller learning rate, but I was trying to have a higher learning rate for the class so that we can finish on time. You tune your learning rate, you tune your hyperparameters, try a different optimizer, don't make sure that your loss kind of gradually goes to 0. But in PDE-based, physics-based neural network, you are bound to see it. But again, it's a hyperparameter tuning exercise that you need to do.
Well, thank you very much.
Yeah, the recording will be shared later on, and we'll try to also post it on the in the book which you have. Okay, was there any Nings, see, you had a question? Okay, any other questions on chat? Initial conditions as probability density functions. Could you give me an example? Like, I want to think. we could define. You could generally define any function as a constraint as well. So I would assume it's not as a probability density function using just this method. I would have to do like Pyro or probabilistic programming language if I were to use PDFs as my boundary conditions. Yeah, so those physics-informed neural network alone will not solve it. So you would have to do like probabilistic machine learning models. There are Gaussian process models which can do it. Bayesian neural networks can do those type, and you can combine Bayesian neural networks with physics-informed neural network to achieve it. Whatever I showed right now will only work for continuous functions or discrete values. You would have to do PPL, probabilistic programming language, or Bayesian Gaussian processes to do distribution-based behavior. If I'm dealing with binary classifications, should I use one or two nodes in the output layer of my neural? It will be one. If you're doing a classification, it's typically like one node is the output, and the node will give you any value. So you can use like even sigmoid function or tanh function as your output layer. And if it's a tanh function, you would just cut it in the middle as your threshold and say anything below that is 0, anything above that is 1. So that will be class 0 or class 1. So you typically have thresholds to classify. So most of them actually do regression and use thresholds to do the classification. So ideally, like the performance will not decrease, the training time will increase, but the model will be able to do better with more constraints. So you're basically saying with these boundary conditions or with these PDE, in that case, the PDE was through the entire domain. Previous example was just boundary. We are enforcing those constraints, so your model should generalize better, and that's the idea of physics-informed machine learning. Right. I would say, like, if you have more questions, you can ask us on Slack. So do join us there, and I'll be able to answer more questions there. All right. And thanks, Tracy, for staying with me today.
Sure.
All right. Thank you, everyone. Do I stop recording?